All right, we're going to do a little fluids lesson, fluids review here today. And we break this into two parts. We have static fluids, and then we have fluid dynamics, or moving fluids. So with static fluids, our basic concepts that we need to know about are pressure and force of buoyancy. And then with moving fluids, we're going to talk about continuity and Bernoulli. So we'll start out with some easy intro equations, some review here. Density becomes important with force of buoyancy, and it is simply mass over volume. All right. Another important easy equation here is the basic pressure equation. Pressure is a force spread out over an area. All right, and remember, units are the Pascal, PA. All right. So this is in general. This would be if we knew some force and we had some amount of square meters, we could calculate the pressure. All right, now for fluid pressure, we have a special equation, and this is for fluid at a depth. So let's draw a little diagram over here. Let's say we have some tank and we have some object submersed in that fluid, and we know the height from the top of the liquid to, let's say, the center of the object. And let's say we want the absolute pressure. The absolute is the total pressure. Okay, and it is equal to the atmospheric pressure plus rho GH. Okay, so this is the pressure of the 40 kilometers of air above us, and of course it keeps going past that, but that 40 kilometers of air is most of our atmosphere's weight, and that is 1 times 10 to the 5th. This is equal to 1 atmosphere, and it is on your constants page, so you don't have to memorize it. Oh, and by the way, that's Pascal, sorry. You can always look that up. Okay, now the fluid pressure is what we call the gauge pressure. This is from the fluid. So if you're asked for the gauge pressure, it means that they just want that. You're going to not pay attention to the atmosphere. So it depends on 3 things. Density of the fluid. Okay, so this density, not the density of the object. And so you might be given a couple densities and have to decide which one is important. G, all right, depends on what planet you're on. All right, and height is always measured from the top to the object. Sometimes you might be given some height right here, and again, you're going to have to know which of these heights to use. Okay, basic fluid pressure equation. Next important equation, force of buoyancy. Rho VG. Now notice that these equations look kind of alike. People like to get these confused. I guess they don't like to get them confused, but they do get them confused a lot. So just pay attention to that. They look similar. This is probably the most commonly missed thing with buoyancy. For our density and our volume, rho Vg, this is for the fluid displaced. Okay, so for this object right here that's submerged, there's a force of buoyancy on it. And by the way, there's a force of buoyancy on it even if it is sinking. Okay, a common misconception is something that is sinking doesn't have a buoyant force on it. Okay, it most certainly does. Anything that displaces a fluid has the force of buoyancy acting on it. So the density is the density of the fluid we're in, and the volume is the volume of the fluid that we are displacing. Okay, and that gets tricky when we start to have an object that is not fully submerged. Here, the volume of the object is same as the volume of the fluid displaced. So there's not really any questions. But what about for a floating object, like we'll do here? We'll check that out in just a second. Okay, so this whole page, I looked through AP tests and different questions, and I pretty much found any free body diagram they could throw at us. Okay, so these are all of the situations that I found where we could be asked about force of buoyancy. So we'll go through these, and what we'll do is simply draw some different FBDs and talk about maybe what could be asked and what the misconceptions would be. Let's start with this one here. So let's say we have a floating object. Alright, like a ball or something like that. And we've got a water level right here. And we need to analyze buoyancy on this thing. Okay, so a couple things. For a floating object, we can say F net, or the sum of the forces is equal to 0. Okay? Now if we had a boat or something, you could have a net force in the x direction, accelerating the boat, but the vertical F net, or the vertical forces sum, is going to be 0. Alright, so if we draw the free body diagram on this, we are going to have mg acting downward. You might use W for your symbol. And we have force of buoyancy acting upward. Now notice that I drew those the same length, and that's because F net is 0. They have to be the same length. So for all floating objects, that F net in the y direction is 0. So I can go down here and I can say that the weight is equal to rho vg. Alright, now a couple cool things here. First of all, we can get rid of little g, and we can say the mass of the object is equal to density volume of the fluid displaced. Okay, and density times volume is mass. So the mass of the object is equal to the mass of the fluid displaced. And that is true for floating objects. Okay, now something else we can do here is we can replace, so off to the side we have density is equal to mass over volume. So mass is equal to density times volume. And so I can replace the mass for the object right here with density of the object, volume of the object is equal to density of the fluid, volume of the fluid. Okay, and let's put this into fraction form. You can say density of the object, density of the fluid is equal to volume of the fluid over volume of the object. Alright, now this side right here is pretty important. Okay, I actually haven't seen this side of the fraction used very much, but this is what I call the sunken fraction. Okay, so let's make some waves here. And then I'm going to rewrite the same fraction. Density of the object, density of the fluid. Okay, so I call this sunken fraction. Okay, and it will tell you the percentage sunk for the object. So I like to do these waves here. Okay, so it's like we have an object floating on a fluid here. All right, kind of clever, right? So percent sunk if we multiply it by 100, of course. And all we have to know are the densities. So that ratio can be kind of helpful for some different things. All right, some more important FBDs. Let's look down here. Submerged and rising. So we've got a water level here in a tank or something like that. And let's say we've got the same ball here as we had in this example. All right, now if it is rising, then the force of buoyancy has got to be bigger than mg. So if it's the same object that we have here, now we are displacing more fluid. So the force of buoyancy on an object can change. All right, so if it is floating or submerged, we can have a different force of buoyancy because it is displacing a different amount of fluid. All right, now that we have a free body diagram, we could talk about F net. So F net is equal to the force of buoyancy minus mg. And we could say that MA is equal to rho Vg minus mg. Okay, now remember, these are for the fluid, this is for the object. Okay, and we could solve for different things here. Free body diagram and then Newton's second law applied. Okay, what if we have something sitting on the bottom? Okay, so down here, let's say we have a chunk of metal or a block of some kind. Let's draw the free body diagram for that. So we are going to have mg acting downward, and we're going to have force of buoyancy acting up. But mg is bigger than force of buoyancy. Okay, now F net is still 0, so we're going to have another force canceling out mg, and this force gets forgotten a lot, especially when fluids are put into the mix, and that force is normal force, Fn. Okay, so F net equals 0, and that's the force of the glass or the bottom of this tank pushing up on the block, just like if we have something resting on a table. F net equals 0, so we can say force of buoyancy plus force normal is equal to mg. And we could be asked to solve for any of those things there. Just taking a look at each free body diagram and understanding the differences here. Okay, now let's put tension into the mix. Let's say we're hoisting something, so we've got that same object as in the previous example, some piece of metal, maybe something being pulled up from the bottom of the ocean or something like that. And it's got some mg acting downward, and force of buoyancy is helping us lift this thing. That's why things are lighter in water. Okay, they're not really lighter. All right, it's just that force of buoyancy helps us out. So we've got force of buoyancy acting up, and then let's say we got a cable right here. Okay, acting along that cable is going to be tension. And the force of tension could be greater or smaller than the force of buoyancy depending on the density of this object. Okay, but usually if we're going to pull something up from the bottom of the ocean or something like that, we are not going to accelerate it. So again, F net equals 0. And we can extend that by saying force of buoyancy plus force of tension is equal to the weight of the object. Alright, submerged with tension again. Let's say we are back to having something less dense than water. So the ball, and let's say it's connected to the bottom somehow. And we need to diagram all of the forces on it and come up with a net force equation. Okay, so in this case we have mg acting downward. We have tension acting downward as well. Capital T or FT, whatever you want to use for a symbol there. And then we've got force of buoyancy acting up. Okay, and this thing's not going anywhere, so again, net force is 0. And I know a lot of teachers use sigma instead of writing out F net. So I'll do that this time. Sum of the forces equals 0. So force of buoyancy is equal to mg plus the tension. Those are all of the situations I saw that we had to analyze force of buoyancy. And I also noticed that usually when we're asked about force of buoyancy, we have to do some type of free body diagram and analyze other forces along with it. So hopefully that helps out and we can apply that to some problems. Here are 3 good ranking task exercises that go with what we just learned about buoyancy. While you're doing this type of work, couple things to keep in mind. Number 1, these 3 problems, I want you to kind of compare them, see what is sort of the same about each of the 3 and what is different about them. Also, an important skill when working on these is trying to figure out which information given actually matters and what information is irrelevant. So keep that in mind. Do all 3 and also put a reasoning for each. Do the part where it says explain your answer. And you really don't have to write a lot for these 3 because they're pretty simple. One of them I did in 1 sentence. The other 2 I think I wrote 2 sentences, maybe 3. And there wasn't anything else I could really talk about. So yeah, 1 to 3 sentences on these. Try them out and then we'll go over them. Okay, here are the answers. First one is like this. Alright, so these are ranked strictly by the mg for each object. So the ones with the most mass in grams are going to get the greatest buoyant force. Alright, and the reason why is because they're floating. So with a floating object, F net, or the sum of the forces in the y direction, has to be 0. So the force of buoyancy must be equal to mg. So if they're floating, the ones with the most mass have to have the greatest force of buoyancy to keep them floating. Alright, and that's really all we need to talk about. One other thing, the volumes of the blocks are irrelevant. That might be an important thing to note here. Okay, let's go on to the next one. This time they involve tension, and we dealt with that in the notes section of the video. So here's the ranking. C has got the greatest tension, and B and F are tied. Then we got ADE. Okay, so here's the deal with this. The force of buoyancy is equal to the mass of the fluid displaced. Okay? I should probably not say equal to. I'm going to change that, and I'm going to say proportional, directly proportional to the mass of the fluid displaced. If we wanted a true force, we'd have to do mg, all right, of the fluid displaced. So anyway, the ones displacing the most fluid are going to have the greatest buoyant force on them. But that's not what we're ranking. We're actually ranking the tension. So we need to figure out a way to calculate the tension for each one. And the tension is equal to the, down here I said, the difference between these two gives the tension. All right, and here's why. If we do a free body diagram on any of these, we've got mg acting down, we got force of buoyancy and tension acting up. Okay, so force of tension is equal to our mg minus our force of buoyancy. All right, and that'll get us our tension. So that's all I did, was I took the mass of each one and I subtracted out the force of buoyancy. Okay, now how did I get the force of buoyancy? Since this is water, 1 centimeter cubed is equal to a gram. All right, so we can just take all of these volumes right here and say that that's also grams of water displaced. And then if we just keep everything in grams, we'll get our tension in grams, which is not really a force. But it will tell us which tension is the greatest. All right, last one. This is probably the easiest one. And there's the ranking. We are ranking greatest buoyant force. And I said the force of buoyancy is proportional to the volume of displaced liquid. So whichever ones are displacing the most liquid have the greatest buoyant force. So we are strictly looking at their volumes here. Their masses are irrelevant. All right, so B would have the greatest because it is displacing the most water. What we're about to do here is probably about the most mathematical stuff that we will see on the Physics 2 exam. Physics 2 exam loves to ask us questions that say describe this or write about that, explain, justify, okay, and they get pretty snotty about us writing about physics. Okay, now on fluids, especially with fluid dynamics, they do get pretty mathematical with the questions. So this is an old Physics B question, which used to be a lot more mathematical than Physics 2 is now. So you're going to see that there's a lot of calculating here in this section. All right, and we'll kind of work through this a little bit together, and then I'll ask you to pause and do some stuff on your own. So here, let's do this. Do part A and then start part B. See if you can come up with the main concept that you're going to need for part B, and we'll go through the equations and the physics of this as we go through this problem. I haven't given you any notes on this part yet, so pause the video and do part A and start part B. Okay, here's what's going on. They ask us to calculate the volume rate of flow for this fountain. Okay, now on your equations page, there are two equations here that deal with moving fluids. This is called the continuity equation, and this is called Bernoulli's equation. So in this first part, we are using continuity, but we are only using half of the equation. If we have a 0.1 and a 0.2 and a pipe is constricting, okay, like if we have some pipe like this and it's constricting or it's expanding to a bigger pipe, there's some kind of fitting there, the equation of continuity applies. All right, where the A's are areas and the V's are velocities. So there's a 0.1 and a 0.2. All right, now in this question, they're not asking us to compare 2 points. They are asking about 1 point, and that's where the speed is 6, okay, which is right here coming out of the ground. Okay, so when that happens, you just use half of the equation. An area times a velocity is a volume rate. Okay, and here's why. An area is meters cubed. A velocity is meters per second. And I just totally messed that up. Meters squared times meters equals meters cubed per second. Okay, so we have a volume rate, all right, a volume over a time. That's a VRF. Okay, so let's calculate this here. Our area is going to be the area of a circle, so we have pi r squared times velocity. Okay, and you can indicate that. I've seen a lot of different symbols used for volume rate of flow. I've seen kind of a swaggy V symbol like that. Okay, that symbol is called nu. It's a lowercase Greek V, I believe. So you can use that if you want. The AP official key uses IV, which I have no idea where that comes from because I is also used for current. So all kinds of ways to indicate that. So if we plug in numbers here, we're going to say our volume rate of flow is equal to pi times our radius, which is 0.015, squared times our velocity of 6. All right, and that should give us, with 2 Sig Figs, 4.2 times 10 to the negative third meters cubed per second. Okay, we haven't talked about this yet, but a word on Sig Figs. AP Physics doesn't really care that much about Sig Figs. If you follow the rules of them, that's fine. But if you're off by a couple Sig Figs, for example, if I put 3 or 4 Sig Figs right there, they're not going to get bent out of shape and take away a point like the AP Chemistry graders would do. With this exception, let's say this is a lab problem and you leave a string of 8 places past the decimal like one of my students always does. Even though I tell her not to, she refuses to round at all. They will take off a point for that if it's a lab-based question. You know who you are, by the way. Otherwise, they don't really care that much about Sig Figs. Just use an appropriate number that's not too ridiculous. Unless it's a lab-based question, you can't be more accurate than the equipment that you are using is the rule of thumb there. All right, so that's the answer. Part B, we are now comparing 2 points. The fountain is fed by a pipe that at one point has a radius of 0.025 and it's 2.5 meters below the fountain's opening. Okay, so down here, let's add to the diagram. There's a pipe down here, and let's label what we know. So down here the pipe is actually bigger, so I'll draw it a little wider, and we're told a little bit about the cross-sectional area. We know the radius, 0.025. We know up here radius is 0.015, and we also know that there's a height difference right here. I'm going to call that a delta y. And that change in height is 2.5 meters. Okay, what else do we know? Nothing else super important yet. Okay, so here's where Bernoulli's equation comes in. I had you start this. What I find is that students see this word right here and they immediately go and try and use this equation right here because you've been taught by your teachers that that is the absolute pressure, which it is. Okay, and my students go straight to this one because they see absolute pressure and they think that it's this equation. Okay, but here's the deal. This actually comes from Bernoulli's equation, and all of the velocity terms of Bernoulli's cancel out. One of the rho gy's cancel out, and we get this. So this really just comes from Bernoulli's equation canceled down. But here's the deal. This only applies for static fluids. When the fluids are moving, then it becomes more complicated. We're going to have to include these terms too. So this is not what we are going to use in Part B. We are going to use the full Bernoulli's equation. Okay? And here it is. So we need to pick a point 1 and a point 2. So let's call this, I like to call our starting point where the water's coming from, point 1. And let's call this point 2 up here. And you may have done it correctly and already be done with this. Okay, so we may need to pause again, we may not. All of these terms go with point 2. All of these terms go with point 1. And that's always how Bernoulli's equation works. It is always a comparison of 2 points and what's happening to the fluid at those 2 points. It looks kind of scary. Big, long equation, lots of terms. One term at least always cancels. Sometimes lots more terms cancel or zero out. All right, so what I want you to do is try and finish the problem knowing now that that's what you're going to use. And you're going to run into a problem because you don't know the velocity down here. So think about how you're going to get that velocity for this side and then try and solve the whole thing. Okay, so pause again and I'll show you how to do the problem after you have some time to work it. Let's see how we did. We need to go through Bernoulli's equation and analyze each of the 6 terms and see how it applies to this. Alright, so let's start over here. This is point 1 and this is point 2. So this is below the fountain, this is above. Alright, so P1 is what we want to find. This is the absolute pressure down here. So we want to find the pressure in that stream down here. This cancels out. Alright, we pick a ground 0 and then a point above. So we're going to call this 0 and we're going to call this positive 6. Okay, the exit point. 1/2 rho v1 squared. Is the fluid moving down here? Yes, it is. Okay, so that term's going to stay. P2, this right here is open to the atmosphere. Alright, so anytime you have a point that is open to the atmosphere and not enclosed, that pressure is the atmospheric pressure. Rho gy2, that's going to be our plus 6. Okay, our height above 0. 1/2 rho v2 squared. That is going to be our exit speed that we already know. It's given to us in the problem. Okay, so we're going to start plugging in numbers here. And we're going to quickly find when we get to this term right here. This one went to 0. When we get here, we don't have this speed. Alright, so what are we going to have to do? We're going to have to do a detour. So down here, detour to get V1. And what we're going to use is continuity. So here's the full continuity equation. We'll rearrange it for V1. Pi r squared is the area, so the pi's actually cancel this time. And you should get 2.2 when all is said and done. And so we're going to take this and we're going to plug it in right there. Okay, now with Bernoulli's equation, I like to just plug my numbers into it. I don't rearrange it first because then I have minus signs everywhere and I screw it up. Okay, so if you want to judge me for plugging in my numbers and not rearranging first, I guess you can go ahead and do that. Normally I do, and I even have proof. Look there, I rearranged then plugged, and that's what I like to see on my students' papers most of the time. But on this, I just think it's easier to plug it all in, so I do. Here's all the numbers plugged in. Here is the answer, and there's the answer rounded beautifully to 2 Sig Figs and put into scientific notation. All right. Again, this is the most mathematical I see AP Physics 2 get thus far in the first couple years of offering it. And yeah, good problem here. All right, it's time for a 90s song. This is a good one. It's a deep one. Wow. What can I say? I'm a product of the 90s. All right, your teacher has the answers to all of the 90s songs at the bottom of the key. So if you're curious, ask them. All right, on to the next FRQ. There are basically two types of problems, FRQ-wise especially, that we need to be able to solve. One is, like we just did, fountains with elevation change and pipe diameter change and all that, and speed change. The other type of problem is what I call leaky stuff problems. Tanks that leak with plugs in them, a dam with a hole in the bottom of it or an exit point in the bottom of it, something spewing out water or about to spew out water. Leaky stuff. Okay, so this is a great problem because it first makes you analyze static fluids and then it makes you analyze fluid dynamics. So try out the whole problem and then I'll go over it. Pause the video. Okay, you've done the problem. Here's the answers. So the first part, they'd like us to find the force down here on this plug. So force and pressure are related like this. We're first going to have to find the pressure. All right, and it does not say gauge pressure, or it doesn't say the force due to the gauge pressure or something weird. So we're going to use the total pressure. This thing is open to the atmosphere. So the atmosphere is adding to the force. All right, it's adding to the force on the water, and then the water's force in addition is going to produce that pressure. Okay, so you add the atmosphere in, and you do the gauge pressure by doing rho GH, and it is, 1025. I forgot that. It is ocean water. Okay, and then you should get 3 times 10 to the 5th pascals. All right, and I copied this off my previous key, so that is actually right, even though I just fixed that. Then over here, there's our pressure, there's our area. You get 12 newtons, so some static fluid stuff there. Okay, now calculate the speed of the water as it leaves the hole in the side of the tank. Here we are going to have to use Bernoulli's. All right, and so I'm going to call point 1 the top of the tank, and I'm going to call point 2 the exit point down here. All right, so let's analyze what in Bernoulli sticks around and what cancels? Okay, so P1. P1 is open to the atmosphere. All right, it's 1 times 10 to the 5th. P2, also open to the atmosphere. Even though this is moving, excuse me, it's still open to the atmosphere. So these two terms, this is atmospheric, this is atmospheric, those go away because I've got 1 on each side, and I could subtract this one over there and they would go away. Okay. Point 1 right here does have a height difference. Okay, and since it is at the top, we are going to keep that around. We are going to call this 0 down here. Alright, by the way, notice that we used a 20 right here because we had to do 25 minus the 5, so that's important to realize is which height to use. Alright, so in this case, we're going to call H1 20, not 25. We're going to call it 20 above that. So down here we're going to call H2 0. That's going to go away. Okay, now completely filled with salt water. This is a large tank, okay, and it's 25 meters tall. This thing is huge, and it's got a tiny little spout. All right, so this velocity, as this water comes out, this drains very, very slowly. So what we do in these types of situations is we say velocity is next to nothing. So that cancels out. All right, now down here there is going to be an exit velocity that is worth something. So we're going to keep that around. So you can see that Bernoulli's cancels down quite a bit here. So let's write our new equation. We will say rho g H1 is equal to 1/2 rho V2 squared. Alright, and we love canceling things in physics. The rho's go away, and we want velocity, so we will say V2 is equal to, I'm going to multiply that to the other side, square root it, so square root of 2GH. We can put a 1 there if we want to. Alright, now that should look kind of familiar. Okay, and here's why. In physics 1, if we dropped a ball from this height and it was going past this point, up here it would have potential energy, mgh. Down here it'd have half mv squared. If you set these two equal to each other, these are energy equations. Set these two equal to each other, the m's cancel, and you get the same equation down here. Okay? So it is important to recognize that Bernoulli's equation is actually derived from conservation of energy. If you look at the really boring derivation in your book and you break it down, it actually comes from energy conservation. Okay, but it's in terms of pressure. All right, now we call this Torricelli's. Okay, so now you have all kinds of Italian equations. We have Bernoulli, we have Torricelli, and we have continuity. And we can use all those, and my students absolutely despise it when I do those Italian accents, but I do it just to make them mad. All right, last part. I added this to the question to make us do a little bit of writing as well, and conceptual explaining. Okay, so let's say we put oil in this tank instead of water. Will this the distance traveled by this stream? Okay, so we're talking about this distance, this horizontal range here. How will that change if it's oil instead of water? Okay, here's the answer. It will remain the same. Okay, and here's why. Remain the same because the distance traveled depends on the exit speed calculated in part B By the way, you may do that in FRQs. You may refer to something you did in another part. This exit speed depends only on the height of the fluid above the exit point. And here's me stating what we came up with right here. Okay, so that should do it. Oh, except I guess I better give you the answer here. If you solve this, you should get 19.8 meters per second, all right, for that exit speed. Okay, last problem. This last problem is bonus material. Your teacher may not require you to do this because this problem takes some time, but it's a great one to do because it is a lab-based problem. So I'll give a hint here for part A. Use mechanics. All right, makes it simpler. You will get to fluids down here. This actually goes with part B. Okay, so this first part's mechanics. This goes with part B, and it's a really good problem to try out. Maybe your study session presenter, maybe you could even try it. I don't know, probably wouldn't be time in a study session, but maybe you could try it at school as a cool experiment to actually work out, and maybe you could plan it on here. So just a couple suggestions, and yeah, like I said, bonus material. That's all we got on fluids. Thanks for watching.